Howdy, folks, and welcome to Chapter 5. Chapter 5, we're going to go hard on polynomials. To start us off with, now that we have graph transformations, we can do more with quadratic equations than we could before. And since quadratic equations are kind of the first interesting polynomial, you know, x squared is the first, and then x cubes and fourths and fifths and so on. Lines are technically polynomials too, but they're not as interesting. Let's go in depth with quadratics. So remember, this is a function that looks like f of x equals ax squared plus bx plus c, and the graph is something like a polynomial. I don't know where it's going to be or how fat it is or whether it's flipped, but something like that, a U-shaped curve. Now, I told you that we can write we can get any parabola we want using graph transformations. So we can start, oh, wow, I can't, this again, huh? Hold on, let me rearrange my desk just slightly. And try again. Okay, we can use graph transformations. We can start with y equals x squared, and then we can do a horizontal shift and a vertical shift to move the vertex to wherever we want it. Say we moved it up and to the right to get this one. And then this one looks like it was flattened. We're going to need a vertical stretch. And then optionally, you could end up with a parabola that looks like this. So optionally, we might also need a vertical flip. So the vertical flip, it's going to be, that's where you turn it into negative f of x. The vertical stretch is where you multiply by a constant. A vertical shift is where you add on the outside, and a horizontal shift is where you subtract on the inside. So those are the four transformations we're going to do. And if we start there, we can get any quadratic at all. So let's take a look at the form now. I'm going to say that the horizontal shift, let's say that that's h units to the right. And the vertical shift, let's say that that's k units up. That way I'm not reusing the same letters. So altogether, these transformations look like f of x equals a times, so that's the times on the outside. There's going to be a plus k on the outside. And on the inside, there's a minus h. And the function itself is this squared right here. So I've just told you we can get any parabola with these 3 or 4 graph transformations. If there's a flip, a will be negative. If there isn't a flip, a will be positive. So 3 or 4 graph transformations, but I could represent them with these 3 symbols here, a, h, and k. And I'm saying that any parabola can be written this way. So the question is now that we have both, can I learn anything by comparing this form to this form? Typically, I will call this one on the left standard, and I'll call the one on the right, not general. No, I don't like that term. I always forget which one. I'll call this one vertex form. So standard form and vertex form. And the reason I call that vertex form is if I go h units to the right, and then I go k units up, then the vertex of the parabola, that's the point at the bottom here, has to be at h comma k. So when I have it written in terms of graph transformations, we can read off the vertex really easily. H is the number we subtract inside, k is the number we add outside, and the vertex is at h comma k. So for example, if I drew y equals -3 times x plus 2 squared minus 4, then h is -2, so the x coordinate's -2, and k is -4, so the y coordinate's -4, and that's where the vertex will be. So I'll go to -2 comma -4, and then this parabola is going to be stretched 3 times and flipped. So in the end, it would look something like this. It opens down because it's flipped, and it's really skinny because it's stretched. How do I get from one form to the other? Well, I'd have to complete the square. So for example, if I wanted to graph, let's say y equals x squared plus 6x plus 10. Then I'm saying, well, a perfect square would be x squared plus 6x plus 9, because that's x plus 3 times x plus 3. I know that this 3 has to be half of 6. So 3 plus 3 is 6. So I know that the 3 is half of this 6. And then 3 times 3 is 9 is how I get the third number. So I can break this up and I can call it x squared plus 6x, and the 10 is 9 plus 1. And then this is x plus 3 squared plus 1. So the vertex is at -3, +1. It's -3 because I went 3 to the left right here. Plus 3 is 3 to the left, plus 1 outside is 1 up. What are some other points on this graph? Take a look at this. When I draw a normal y equals x squared parabola, the parent function, 0 squared is 0, 1 squared is 1, and -1 squared is also 1. So the average rate of change from 0 to 1 is 1. There's like a V in here. This has a slope of 1, and this has a slope of -1. That should be a right angle at the bottom. So as long as your parabola doesn't get stretched or shrunk at all, this V is going to stay the same shape. So if I go 1 up, if I go 1 to the right, I go up by 1. If I go 1 to the left, I go up by 1. So if there was a grid drawn, these boxes would both be unit squares. So here, there's no stretch or shrink, there's no A out in front. And so my vertex is at -3, 1. I'll go 3 to the left and 1 up. And then I can draw in those two boxes if I want. I'm not going to need them every time at all. But this is -3, 1. Then this will be 1 to the right, -2. And this will be 1 to the left, -4. And they'll both go 1 up. So 1 plus 1 is 2. And so those are two other points on the parabola. And it looks like this. If I wanted, the graph of, let's say, -4x squared, y equals -4x squared, minus, let's say, 8x, and then minus 10. Oh, not 10, 6. Let's do it like this. Y equals -4x squared minus 8x minus 6. That's a bit of a mess. So what I'm going to do is I'm going to pull out a -4 just from the first two terms. Like so. Okay. Now I see two terms that I can make into a perfect square if I do my +1 -1 trick. X squared minus, whoops, this should be a plus. My goodness. You see why that's a plus, right? I pulled out the minus sign when I pulled out the 4. So I know that there's a perfect square. X squared plus 2x plus 1 is x1 squared. And so I'm going to do x squared plus 2x plus 1. Now I added the 1 in the parentheses, so unfortunately I have to subtract the 1 in parentheses. How will I resolve that? Well, it's not too tough. I'll distribute the -4. This is goofy, but watch along. I'll distribute it to these two. So the first three terms, I'll keep the -4 factored. The last term, -4 times -1, is +4. So now our equation looks like this. And what that gets me is I have -4 times x plus 1 squared, and then +4 minus 6, that's a -2. So First off, the vertex is at -1, -2. So 1 to the left and 2 down. This goes 1 to the left, this goes 2 down. So here's my vertex. Now, this -4 is indicating we are flipped and we are stretched 4 times. So when I go 1 to the left or right, instead of going 1 up, I'm going to go 4 and I'm going to go down. I could draw the boxes here if you want. These got stretched out. It's 4 times as tall and skinny as it was before. So if I go 1 to the left or 1 to the right, either down to -2 or, oh, I guess this is up to 0, I have to go down 4 from -2 to -6. And this parabola is going to be real skinny. Going to look like that. Okay? So that's how we graph parabolas. Let's see. It would be nice if we, sorry. One more thing about the vertex real quick. If the parabola is upside down like this, it's increasing until the vertex. The vertex is the local and absolute maximum, and then it decreases after. The vertex is also the turning point. But that point right there, we call it the vertex. Okay, anyway. Completing the square here was a little bit of a pain in the butt. It would be kind of nice if I could graph the parabola without completing the square. How would we do that? So we have standard form, and that's y equals ax squared plus bx plus c. What can I possibly do to find the vertex? As a matter of fact, there's a very simple answer. One moment. Okay, as a matter of fact, there's a very simple answer. I know where the roots are. The roots, the zeros, the x-intercepts. These three mean the same thing. I know where they are. I can use the quadratic formula. I know that the roots happen when y equals, when x equals -b plus or minus the square root of b squared minus 4ac all over 2a. I'm going to rewrite this just slightly because there's a point I want to make. You know, if I have 1/4 plus 2/4, I can write it like this, or I can write it like that, right? I can write that either way. I'm going to do that transformation here around this plus or minus. This, go. 5 seconds of lag, class. How great is that? I'm going to do this same transformation here. I've got 2 terms in the numerator, and instead of writing 1/2 plus 2/2, or sorry, 1/4 plus 2/4, I'm just going to write the first fraction, -b over 2a, plus or minus the second fraction, root of the discriminant, over 2a. We talked about discriminants back in chapter 2. Okay, so when I write it like this, these are the x coordinates of the 2 roots. Now take a look at this, take a look at this parabola. Let's say it's upside down and it's a big one like this. The thing is, every parabola, no, let me start that sentence differently. You remember that y equals x squared, the parent function? It's an even function. It has horizontal symmetry. If I put a mirror right down the middle, its mirror image is the same as the original graph. Now, when I changed that into this graph, all I did is move it around and stretch it and flip it or whatever. None of the things I did, none of my graph transformations can destroy that symmetry. Now, the mirror has moved because the mirror still goes through the vertex. But since it's always symmetric through the vertex, I'm thinking if I put a mirror right here, you see, the graph is perfectly symmetric across the mirror. Every parabola does that. Not every polynomial, but every quadratic, every parabola, every second degree polynomial, ax squared plus bx plus c, has that symmetry because it's descended from the parent function that has that symmetry. So now take a look at this. The way I've written these roots, look at this on a number line. If I go up, I'm going to the right. If I go down, I'm going to the left. So this says I could start at negative b over 2a and go up by the square root of the discriminant over 2a, or I could go down by the square root of the discriminant over 2a. I'm just writing d for b squared minus 4ac here because I don't want to copy that a million times. So what that means is this point right in the middle, since I went the same distance, this point right in the middle has to be negative b over 2a, comma 0. And I can go up by the square root of d over 2a, or I could go down by the square root of d over 2a. So these are my two roots. Negative b over 2a plus root d over 2a, and negative b over 2a minus root d over 2a. This is saying start at the middle, up or down by the same distance. So go 5 units to the right and 5 units to the left from your starting point of negative b over 2a. Okay, but if these points are both the same distance from the middle, and the middle is negative b over 2a, then the vertex has to be at negative b over 2a. So what we've just learned is that the x-coordinate of the vertex is always negative b over 2a. Has to be, because it's symmetric around the vertex. That's why we go up or down by the same amount from the middle to get to the two roots. So the middle has to have the same x-coordinate as the vertex, because they're straight up and down from each other. So that's where the vertex is. Now we know how to find the vertex in quadratic form. Like, for example, in this problem back here, negative 4x squared minus 8x minus 6, the way I'd get the vertex is x equals negative b over 2. So b is negative 8, and a is negative 4. So 2 times negative 4. Negative 8 over negative 8 is 1. So the vertex happens, whoops, missed a minus sign. There should be a minus sign on the outside here. So the vertex happens at negative 1, which is what I have in the picture. Thank goodness they're consistent, right? I did not just break math. It's negative of b over 2a, and b is negative 8, and a is negative 4. So there's 3 minus signs here. So that's where our vertex is, just as predicted. Or this one right here, x squared plus 6x plus 10. The vertex is at negative b, so negative 6, divided by 2a, divided by 2. So the vertex is at negative 3. And sure enough, the vertex is at negative 3. How do you get the y-coordinate? Well, it's simple, really. If I know x equals negative b over 2a, which is negative 6 over 2 times 1, which is negative 3, then the y-coordinate of the vertex is x. So it's negative 3 squared plus 6 times negative 3 plus 10. All I did is plug the x-coordinate into the function to find the y-coordinate. And you'll find that this is 9 minus 18 plus 10 gets you 1, which is this number here. So that's how you find the vertex. Pretty handy. So if I had a nasty polynomial, I didn't want to complete the square. Like if I have f of x equals negative 2x squared plus 5x plus 4, I know from experience that completing the square is going to get nasty really quick. I'll factor out the 2 and have a 5 halves here. And then I'll have to split that in half and square it, so I'll have a 25 fourths, and that sounds like a nightmare without end. So I won't do that. Instead, what I'll do is say, vertex has x equals negative b over 2a. So it's negative over 2 times negative 2. Well, that's 1.25. So that's where the vertex is. What's the y-coordinate of the vertex? Let's find out. 1.25 gets plugged into f, so that's negative 2 times 1.25 squared plus 5 times 1.25 plus 4. Turns out, might as well use a calculator here, that happens to be 7.125. So now when I'm graphing this guy, just like that, I can put the vertex at 1.25, comma, 7.125. But where does the rest of the curve go? Well, that's easy too. This a is the same a when I write, whether I write the polynomial in standard form, whether I write it in standard form or in vertex form, the reason I used a for both is this a is the same. A tells you whether you have a flip and how much you should stretch. So down here, a is negative 2. That's telling me I do have a flip because it's negative, and I'm going to stretch by a factor of 2. So when I go 1 to the left or right, I'm going to go 2 down because it's flipped and it's stretched by 2. So 1 to the left or right means I could go up to 2.2, or, oh, I need more space than that, or down to 0.25. And then down by 2 means I go down from 7.125 down to 5.125. So I can plot those 3 points, and from there it should be pretty easy to draw the rest of the curve. Oh, one more thing. If I plug in x equals 0, I get 0 plus 0 plus 4. So I know that this point, 0, 4, is also on the graph. That way I know where I'm hitting the y-axis. So the rest of the curve looks something like that. I missed a little bit. Should be over here further. Oh well. The graph looks like that. I don't know exactly where the roots are, but I could find those with the quadratic formula if I cared. That's how you graph a polynomial, and notice I never had to complete the square. So if I had, it would have sucked. This is a much easier way. All right. So that's the first half of the video. Next, we're going to use vertices, especially, in a handful of applications. I think we'll do 2 good problems, maybe 3. I'll see you in a moment.